Hello guys, you're welcome back to class today. Today we are going to be considering a topic that is connected to what we did in the previous class, although just a continuation. And the topic is units and measurements. Units and measurements. Now, it is important for us to note that no physical quantity is meaningful unless it can be exactly measured or quantified. So for that particular reason, the quantities that are measured in physics are divided into two parts. Number one is a number. This number states the size of the quantity that is being measured. And number two, a unit. And what this unit does is that it identifies the quantity being measured. For example, if I say that the length of a table or the length of a book or the length of a certain material is 5 meters, what does that mean? For me, putting meters means that what I am measuring is length and not mass. If I just say 5, it doesn't tell us about what is being measured. So the unit is important in order to give the student an idea of what is being measured. So if I say 5 meters, ordinarily what should come to your mind is that what is being measured is the length. So if I'm measuring mass, for example, and I weigh something and it gives me 15 kg. So even if I didn't tell you that it was mass I measured, once you hear 15 kg, what comes to your mind is that it is mass that is being measured. So 15 tells us the number or the magnitude of what is being measured. Then the kg there tells us about the particular physical quantity that's being measured, and that is what the unit is. So having said that, there are basically two categories of quantities that we have in physics. Number one is the fundamental quantities, and then number two is the derived quantities. So I'm going to be telling you what fundamental quantities and derived quantities are, and then I will state their units and then their derivation. So let's go. Number one, fundamental quantities. What is fundamental quantities? Fundamental quantities are the basic quantities that are independent of others and cannot be defined in terms of other quantities or derived from them. What that means is that they are the basic quantities upon which most quantities depend on. Likewise, fundamental units are the basic units upon which other units depend. They are the units of the fundamental quantities. What that means is that fundamental quantities and their units can stand alone. They don't depend on any physical quantity whatsoever for their derivation. They are stable. They can stand on their own. I'm going to give you examples of fundamental quantities. Number one, the length. I'd already mentioned that in our previous class. The length that is, and the unit of the length is the meters. Meters can be represented using letter M, small letter m, and the dimension for length is capital letter L. I'm going to be telling you about dimension shortly. Number two, we have the mass. Mass is measured in kilogram, and that is represented in kg. The dimension for mass is capital M. It's important for us to know that there are other units of measuring mass, like the tons and so many other units of mass. Number three, we have time. Time is defined as that in which events are distinguishable with reference to before or after. So it is measured in seconds, and seconds is represented using small letter s. The dimensional symbol for time is the first letter, which is capital T. However, there are other fundamental quantities also, but these three are referred to as the basic fundamental quantities. So I'm going to finish up the list. Number four, we have the electric current. Electric current is measured in ampere. Ampere is represented using a capital letter A, and the dimensional symbol is capital letter A. We have temperature. Temperature is measured in Kelvin. There are other units for measuring temperature, the Celsius and the Fahrenheit. Kelvin is represented using capital letter K. The dimensional symbol is theta. I know you've been hearing that, theta. We have number 6, the amount of substance. Amount of substance is measured in mole, which is represented as MOL. And then luminous intensity. Luminous intensity is measured in candela. Candela is simply represented using small letter CD. So these are the fundamental quantities that we have. Every other quantity that you know about depend on these particular quantities for their derivation. I believe you've heard about velocity. I believe you've heard about acceleration, force, pressure, work, power, moment, and so on and so forth. All those ones, they get their derivation by the simple combination of these fundamental quantities. So these ones I mentioned now are referred to as derived quantities. They are derived from the fundamental. So in essence, generally, fundamental quantities, they can stand on their own. They don't depend on any physical quantity for their derivation. 2. Derived quantities and units. Now, derived quantities and their units are those that are obtained by some simple combination of the fundamental quantities and their units. So what that means is that if I combine two or more fundamental quantities, I could get a derived quantity. So by implication, they are dependent on the fundamental quantities and their units. For example, area. I believe you've heard the word area before. Area is simply the product of length and breadth. Now, both of them are all lengths, right? So the unit of area is meter square because both length and breadth are represented as length. That is, it is a way of representing length. We have the volume. Volume is simply the length times the breadth times the height. So it means that the unit is meter cubed, telling you that both the length, the breadth, the height are all measured in meters, which is length. Now that we have derived volume or confirmed that volume is a derived quantity, density is simply the ratio of mass and volume. That is, density is mass over volume. So you know that we had already derived volume from fundamental quantity, and we also know that mass is a fundamental quantity. So density is the ratio of mass over volume. The unit of density is kg per meter cube, right? Now, you can see that all of these combinations are simple combination of one or two fundamental quantities. So derived quantities depend on fundamental quantities for their derivation. So we have other derived quantities. I'm just going to run it down for you. We have the work, we have momentum, we have impulse, we have force, we have acceleration, we have velocity, we have power, we have moment. It's just, the list just goes on and on and on. But knowing these derived quantities is not enough. We need to also know how they can be derived. That is their formula and their units. For example, work is the product of force and displacement. Now, meaning that when you combine force and the distance moved in the direction of that force, we can get work. So we can break down this and derive the unit of work to be Newton meter. Another way of writing Newton meter is what we call the joule. I know they've taught you work energy and power in your junior school, so you have enough experience in this. Momentum is simply the product of mass and velocity measured in kg meter per second. Impulse is simply product of force and time, which is measured in force. They've taught you is mass times acceleration, which is measured in kg meter per second square. Now this kg meter per second square is simply represented using Newton. Acceleration is velocity over time. That's change in velocity over time. And velocity is simply displacement over time, which is meter per second. So acceleration is the change in velocity over time, which is meter per second square. And then power is work done all over the time taken, which is measured in joules per second, or what we refer to as the worth. So I cannot exhaust the list of derived quantities. I had to set this foundation for you so that you can be able to know how that you can derive these quantities. Now, finally, for this class, we are going to be talking about dimensions of a physical quantity. Now, the dimensions of a physical quantity indicate how it is made up in terms of the SI-based quantity. I already mentioned to you that if, the base quantities are the mass, the length, and the time. So in other words, the physical quantity is said to have been expressed in terms of the dimension of these three fundamental units of the length, the mass, and the time for us to be able to represent a body dimensionally. For example, if I want to talk about density, the dimension of density from the derivation or the formula, which we said is mass over volume. I told you that mass is represented dimensionally as m, and anything length is represented dimensionally as L. And since volume is three lengths combined, that is length, breadth, and the height, so it means that the dimension for volume will be L cubed. So if I put that in the formula, I'm going to have m over L cubed, which is now going to give me in indical form ml raised to the power of minus 3. So this is what we refer to as the dimension for density. Now, this also can be used to derive the unit of density, since m is mass and the unit of mass is kg, and then L is length and the unit of length is meters. So it means that I could, from this dimension, derive the unit of density as kg meters raised to the power of minus 3. So you see, so dimensional analysis is important for us in order to be able to express a derived quantity in terms of a fundamental quantity, especially the base fundamental quantities, mass, length, and time. So I'm going to be showing you how that we could be able to get the dimensions for some derived quantities. For example, speed. Speed is distance over time. And you know that distance is a way of representing length. So in other words, I could write it as length over time. Don't confuse this, please. The formula for this speed is distance over time. But because distance is a way of representing length, distance is simply the length from one end to another. So, and then length is represented as L and T is represented as capital T. So the dimension for speed is LT minus 1. So if I substitute the units of this, it will get the formula for speed. Now, both speed and velocity, they have the same dimension and the same SI unit. From velocity, we can be able to derive acceleration. Acceleration is simply the change in velocity over time. So since we had already gotten velocity as LT minus 1 and then over time, the dimension for acceleration is written as LT minus 2. So it means that the unit now, L is meters, T is times seconds, as ms raised to the power of minus 2. We have force, mass times acceleration. So since we have gotten acceleration as LT minus 2, just multiplied by mass, we get mLT minus 2. So the unit of force is kg meter per second squared, which is written as Newton, which is used in all calculations. So I'm going to be asking you some questions to test your understanding quickly. Number 1, show that the dimension of pressure is ml minus 1 T raised to the power of minus 2, and hence derive the SI unit. You can pause the video and work it out yourself. Now I believe that you must have done that. Now look at my solution. Pressure is simply force over area. And if you check what we've done before, force is represented as mLT raised to the power of minus 2 and area is L squared. So if I cancel L up and down, I'm going to get mt minus 2 over L. That will give me pressure as ml minus 1, T minus 2. So the SI unit of force is Newton and that of area is meter squared. So it means that the SI unit of pressure is Newton per meter squared. Number 2 question. Derive the dimension for work. And what is the SI unit of work? If you check what we've done before, you will notice that work is force times displacement, and force is mLT minus 2, and displacement is just a way of representing length. So if I join everything together, I'm going to get ml squared t raised to the power of minus 2. So the unit of work is force times displacement. That's Newton times meters. That's Newton meters. And it can be written as joule. And this joule is the one that is used in all calculations in physics. Now, in order not to make this video lengthy, I'll just summarize and show you a table containing some dimensions of an SI unit of some derived quantities. So take a look at this table. I have here work, which is the same thing as energy, momentum. Also, they have the same dimension as impulse, volume, area, pressure, power, density, and moment. All these are derived quantities, and you can see their dimension represented. So check from what I've shown you now to confirm that these dimensions are correct. So I believe that this has really been impactful. Thank you for staying in. Our next topic would be measurements of length, mass, and time. In that class, I am going to be showing you the instruments that we can use in measuring length and also mass and of course time. And then I will describe them for you, tell you about their reading accuracy and everything that you need to know in their measurement. Until then, do have a nice day.